I guess I should have apologized for not having the test marked before I started the recording, so that there's not video evidence, or I guess sound evidence, but you would have known anyways. But as I was saying, not everyone was here yet. Once I'm done marking, I post the grades right away, so you'll know, and then I hand them back, of course, but that way you'll know. Oh, final exam review. No, getting ahead of myself. Final exam. There, we're ready. We're ready. December 18th from 9 to 12. It is cumulative. It's a 3-hour exam. I'd say I like to make the exams about 2 hours and 15 minutes long-ish. So it's not a 3-hour exam. You've got some time to think about stuff. And so I don't like to make them too long, but you have 3 hours to do it, and then you're free. Okay. Now, what else did I do? I set myself up big time for failure. Let's see here. But we just might pull it off. Where's this week? Here. So we did test 1, check, good. And then I said, okay, we're gonna do what 5.1 and chapter 6 all in one day, including the examples, because there's no example day. So kind of a whirlwind. What did I have to do? Well, I went through, and we're only gonna talk about, there's lots and lots of pretty heavy theory that we could do that I don't want to do because we don't need to. And so if it feels light, it's because I'm serving up what you need and only what you need. And then you can look at the rest later if you want. But even some of the stuff that I'm serving, we could do without, like matrices. But it's nice to have seen. Have you guys seen matrices in your other classes yet? No. Yeah, that's fair. Yeah, that's fair. That's fair. Okay. Let's see here. So I don't want to go too crazy into matrices, but it is really important that you know kind of the anatomy of a matrix. Okay. And although I'm not going to talk about matrix multiplication, I'll show you just kind of what we would have to do, and then we can all agree that, oh, that's way too tedious for us, and then parking lot it and let someone else teach you that. Okay. But first, what's a matrix? Well, it's super fun to say and think about. The Matrix. Although I'm pretty sure I've never seen the movie, which is the time's passed, right? It's game over. Why would I watch it now? I do matrix algebra. So a matrix is a way of representing information, but this is a way where a computer can read it, right? And so usually we have information and we want to be able to give it to a computer. And one of the main ways that we do that is with a matrix. Okay. And so what do? So a matrix looks like this. It's got this, how about arrays? Have you seen arrays yet? Okay, phew. Then it's just a bunch of arrays next to each other. Ta-da! That's a matrix. I know. But because we have, so now instead of just the one column, right? That's an array. Okay. But we also have multiple columns, multiple rows. And so now inside here, we have a subscript I, or I guess M in this case. Sometimes we use IJ, sometimes we use MN. I guess these guys use MN. That's fine. So here, the first entry, how am I going to write this? How am I going to do this here? A11. Actually, okay, fine. 1-1 says that it's row 1, column 1. Okay. Let's do one that's more interesting. Oh, I guess I shouldn't draw over. A23 is the entry in the second row, third column, right? And so this is the entry in row 2, column 3, right? So it's always in the format A row column. Okay, so that's what a matrix looks like. Ta-da. And we can talk about the order of a matrix. The order of a matrix is the number of rows by the number of columns. And so here we've got an M by N matrix, which means that you have M rows and N columns. Okay. So in terms of our matrix, usually we use, if we let A be a matrix, we use kind of big square brackets to denote a matrix. And what we're saying is that we have M rows and N columns. Which means that the order of the matrix is M by N. And you write it just like that, M by N, right? Or M times N, but you read it M by N. Okay. So that tells you the size of your matrix, right? Okay. So the order of the matrix, this tells you the size of the matrix, or the dimension, but sure. Or the dimension. So but I can't keep adding to my own notes. Fine. Dimensions. There. Done. So I think of it as the size of the matrix, right? And we can deal with any size matrix, but let's just start itty bitty here. And if we have a matrix A, right? First entry, second entry, third entry, fourth entry. This is a 2 by 2 matrix, right? So here, this is 2 by 2. B is just an array, right? Because it's 3 by 1. Here, I'll do 2 by 2. D is going to be 1, 2, 3 by 3. Okay. Knowing the order of the matrix is going to help us determine if we can do things like add two matrices. Are these matrices equal? Okay. Which is exactly what you think it is. If a matrix is equal, then they're exactly the same, right? All the elements are the same. And of course, then they would have to have the same order as well, right? And so we can talk about things like, is the matrix A 1, 2, 3, 4 equal to the matrix B 1, 2, 3, 5? No. You don't need to know anything about matrices to tell me that, no, those don't look equal to me, right? The orders are the same, but but they're not equal because these entries are not the same. Not the same. Oops. We've got a proper definition down here. So a matrix A is equal to a matrix B, which we write just the same way as always. A is equal to B if and only if A and B have the same order. Of course, they have to have the same shape in order to be able to be equal, right? And so, right, same shape. And then we can look at all the entries, all the corresponding entries are equal, which, so they do use the IJ. Okay. AIJ is equal to BIJ, same locations. Yeah.
I was going to say, like, let's say A and B have the same numbers, but like the numbers are rearranged. Would that still be equal?
No.
Oh, okay.
No. So for example, let's write that out. If I let A be 1, 2, 3, 4, because I have no imagination, and B be 4, 3, 2, 1.
Yeah.
Not equal. Because the entries in the same locations have to be the same. Good. So here, all corresponding entries are equal. And then you can keep going. Fine. Proper. Right. I is the same for both and J is the same for both. Then you're in the same location, right? It's just generic. Then those two values have to be the same. Oh. We can add matrices and it's fine. Okay, so here, if you have a matrix, and I think this is A, so I'm just going to add that here. Something like this, a little 2 by 2 matrix and a 2 by 2 matrix. If I want to add these together, then it behaves the exact same way that you would think it should, right? 1 plus 3 makes the first entry. 0 plus 4 makes the second entry, or I'm using second sloppily. 2 plus -5 makes the 2, 2 entry. There you go. -1 plus 2 makes the, no, that's 2, 2. This is 2, 1. Confuse myself. Not really, it's just the words. Which you can simplify to another 2 by 2 matrix, right? And so here, this is a 2 by 2, and this is a 2 by 2. That's important because in order to add or subtract, right, they're the same. In order to add matrices, they have to have the same shape so that you can match them up. Okay? And they yield the same shape, 2 by 2. Order, I should say. I think of it as shape, though. I think it's cuter. But proper terminology is order. So if you wanted to add A and B, you can't do that because there's no way to match this 1, 3 element because there is no 1, 3 element here, right? So these guys would get lost. Yeah. So matrix addition by definition is if we have 2 m by n matrices, meaning they have the same order, right, same shape, then A plus B is another m by n matrix, right? Just like we saw, a 2 by 2 plus a 2 by 2 makes a 2 by 2. Just add the elements. Okay. Where the elements of the added matrix are the individual elements from each corresponding location. Okay. Okay. And of course, if the orders of A and B are not identical, then A plus B is not defined. We can't do it. Yeah. Okay. Scalar multiplication. A scalar, is that something, if you've seen arrays, maybe you've seen a scalar multiple or something like that. It's just a constant that we're multiplying, either an array or a matrix. Matrix is like a big brother of an array. And so, or maybe that's just how I think of them. This is just a little bit bigger. So if we have some constant 3, for example, or C generically, and if we let A be this matrix here, this 2 by 2 matrix, we can find C times A just by multiplying the 3 inside onto each of the elements. Yeah. And so 3A is exactly 3 times 1, 3 times -2, and let me just write that here. So 3A is the matrix 3 times 1, 3 times -2, 3 times 3, and 3 times 5. I use square brackets on my matrices, but round ones are fine too, as long as you're stretching them to cover the entire group, I guess. And that's how we got to 3, -6, 9, and 15. So if we want to find C times A, this is scalar multiplication, then we just take C times each entry and find the resulting matrix, which is going to be what order? It's going to still be m by n, right? And so that's good to keep in mind. CA still has order m by n. Each element is just being multiplied by some scalar. Yeah. So matrices are pretty fun until you get to matrix multiplication. You'll see nothing is highlighted in here. I went through and I said, well, do we actually need this for anything? Can we get by without it? We can. So I'm going to talk about it, but we're not going to have to do it. It's just very tedious. We get computers to do it. Usually we need to know how it works. Okay. So if you have 2 matrices that you want to multiply together, okay, and that happens a lot. So I shouldn't undermine the value of it. It's just, we should probably just let computers do it and not do it by hand, because yikes. You'll see. Okay. So if I want to find the product, words, of A and B, some of the things that I have to keep in mind are that to multiply A and B, the number of columns in A has to match the number of rows in B. If A is m by n and B is n by p, I guess. I don't know. Run out of numbers. Yeah. Then A times B is M by P. Okay, so they have to match kind of in the middle. They have to join up. Okay? That's the first thing is M by P, which means I'll just highlight here that they have to kind of match up. Otherwise, you won't be able to multiply them. Okay? And then the result is going to be the size of M by P, the outside terms, right? Good. That's just the order of it. Now, what do we have to do? Okay. Matrix multiplication looks like this. Goes a little something like this. So if you have your first row, to find the first entry, which would be this entry here, you would take this row times the first column, and you can overlay them like this. This one's using the second column, so just to show the middle section. Okay, so what you do is I take my hands and I kind of block them like this, and then I lay them on top of each other, and I find the products and I add them all up. That's confusing. Those weren't math terms, right? But what are we doing? So we take 1 times 2 plus -1 times 3 plus 0 times 4. That sum takes the place of the middle entry, or this entry that we're looking for. Okay. Yikes. We're not going to do it, but now we're happy that we're not, yeah? Okay. So of course, a 3 by 3 matrix. This is a 3 by 3 matrix, and this is a 3 by 3 matrix. I think of it as, okay, the result is still going to be a 3 by 3 matrix. I'm allowed to multiply these because they match up here in the middle, right? But the result is going to be a 3 by 3 matrix. Okay. There's a lot of work in there, though. Yikes. Okay. So let's just, for fun, write out what this entry would be. This first entry would be the first row. That's the same, which is 1 times, and then we want the first column, right? 1, 1. First row, first column. Here we go. 1 times -6 plus -1 times 3 plus 0 times 1. So that entry is going to be -6 minus 3, so -9. So here we found that this one's -9 here. And then you'd have to do that, and you'd methodically move through the columns, move through the rows. How are you going to find this entry? Now you're going to shift it down. Now you're looking at the second row, first column, second column, third column, and that's a lot of work. So we're not doing it, just talking about it. This is me just talking about it, doing it just a little bit. Question? Yes.
So why is it using row 1 and column 2?
Oh, it just picked something that was nice to print out like this. So it's talking about row 1, column 2, which is the 1, 2 element, which is this one here. So that's they're just using it as an example. But this one makes that one the 1, 2 element. Unless I did.
How do you find the one under the pink circle again? What would that be? Would that be
This
row?
This one here.
Yeah.
That to get that one. Oh, now you're asking the tough questions. Okay. Okay, to get this one, you want the
Second row.
second row, first column. And then you move down. Okay,
Wait, is all that up there just one element? Okay.
yes,
Oh,
all that math for each element. It's not a lot of math. You could do
yeah,
it.
it's like a 5 by 5 matrix, trying to multiply by the 5 by 5 to sit there all day.
Yeah, exactly. Yeah. But I mean, aren't you grateful for computers? They just whip them up. Whip them up. It's good to know what goes into multiplying matrices, but like I said, I'm avoiding anything that requires it. It would make some shortcuts, but I'm a brute force type of gal anyways, so no shortcuts for me. All right, but I mean, they outline them all and you can read about them when you find a spare moment. Okay, so we all agree, yeah, we're grateful to not be doing matrix multiplication. Addition, scalar multiplication, that seems like a gravy train now, right? Yeah, we're good. Oh yeah, take me back there. I didn't pick any exercises because right away they want you to multiply matrices, make you work for it, which you're welcome to try, right? But maybe try something like, we can do that. Why not? Let's do that. Where am I going to put it? Put her there. Where? Maybe here. So we've got A, B, and C, and then I'm going to snag just one for practice. Aren't you glad you don't have to do this? What would you have to do here? A times B, then find that, take that times C, and then show that that's the same as B times C, and then A times that. That's a way to spend an evening, right? We're not going to do that. Did I snag this already? I think so. At least you know they should be equal. So you know what you're working towards, I guess. But man, oh man. Okay. If C is 3, this we can handle. We want to show that C times A plus B is the same thing as C times A plus C times B, right? So does it distribute properly, right? Just the way that we expect it to. That's the distributive property, right? And so that's what we're checking. And so let's do what we do. First, I'm going to find A plus B. Why not? Okay. So A plus B is, I can't bring myself to do the round brackets. Sorry, guys. I like to have the forceful closure of the square brackets. A plus B, now we're back to 1 plus 0. I'll write them out. Oops. In the completely wrong order. 1 plus 0 is the first element, then, or the 1, 1 element, the 1, 2 element is -1 plus 1. The 2, 1 element is 2 plus 3. It's harder to say than to do, I think. The 2, 2 element is 3 plus -5, which is 1, 0, 5, -2. if I want 3 times that, 3 times A plus B, that's going to be 3 times 1, 3 times 0, 3 times 5, and 3 times -2. Oh, that was sloppy. Sloppier than usual. 3, 0, 15, -6. Okay. Just a little warm up. All right. Let's do it all over again. We want to show that that's the same as 3 times A plus 3 times B, right? Doing it individually. Oh, maybe I can scoot these over. Can I? Can I? Can I? Maybe. How about 3 times A? Can I just do it? I think we're there. 3, -3, 6, and 9. Unless I did something wrong. 3 times B. Oh, that one's 0, 3, 9, -15. Oh boy. So now I want to show 3A plus 3B is equal to what? 3 plus 0 is 3. -3 plus 3 is 0. Hey, so far I'm feeling lucky. 6 plus 9. All right. 15. 9 plus -15. I'm going to guess is -6. But who knows, right? I hope 9 plus -15 is 6 or -6. Really hope. Yay. Therefore, 3A plus B is the same thing as 3A plus 3B. Little matrix, stretch our legs. Show them what we've got. Yeah. But that's as far as we're gonna go in terms of manipulating matrices. Could subtract them, I guess. But you can do that. Okay. All right. Any questions about matrices in general? They're good to have up our sleeves, but yeah. Well, you guys have all these like different doubles. Doubles mean something. I know that.
A double array is just like an array instead of that's like multiple arrays. It kind of looks like.
I feel like if it was a matrix, they would call it a matrix. But I don't know.
They just arrays, grid arrays. I don't think so. You just multiply grid arrays together.
Okay.
Most likely how to do it.
Okay. I guess the answer is I don't know. Double arrays, I don't know. I know matrices though. Although it's been a while. Man, oh man. Okay. Is there another one in here that we could use? Oh, cute. I guess for practice, you could show that C plus D times A is the same thing as C times A plus D times A, but that's basically the same thing that we just did. So I'll highlight it and leave it with you. Could do a couple more, but okay, now I'm carried away. There we go. That's enough. That's enough. relations. Okay, so we needed matrices because later on, they've got these kind of, can I say that these are kind of weird poems? They're weird, right? I don't really get them. Maybe I'm not mathy enough, or maybe I'm not artsy enough, but I don't know. Yeah, I don't know. But anyway, I think it's cute that they have these, and maybe there's not a lot of poems about math out there in limerick form, nonetheless. An adjacency matrix will show where the edges between vertices go. For a nice simple graph, you can cut through the chaff, knots and ones in symmetrical flow. I think I screwed it up around here. Right? Okay, so relations. We're gonna do kind of bare bones relations because you're gonna see it again in 251. Okay, and so we're just introducing it here, and we're gonna just use ordered pairs. That's nice. You'll thank me later. So what's a relation? If we have A and B, now they're sets. They're no longer matrices. So A and B are just two sets that we have. Then a relation from A into B is any subset of the Cartesian product of A and B. Uh-oh. Oh, dang. That's when we had to match up all the elements of each set, right? And so that's when we had something like, and brace yourselves, it's going to look like a matrix because it is. If you have A has the set is, let's do 1, 2, 3. That's a nice set. B, let's let it be 4, 5. What was the Cartesian product of this thing? Well, it was, so A times B, remembering that these are not matrices, right? What a mess. Is going to be the set of 1, 4, 1, 5, right? We're doing all the mashups, right? With the first element from A and the second element from B. And 2, 4, 2, 5, 3, 4, 3, 5. Okay. Now a relation is any subset of these ordered pairs. Okay. So let's write that down. A relation is any subset of these pairs. I should say ordered pairs, but ran out of space. Hey, here I think I'm being original, and it's exactly what they have for us. Simple example. Well, just goes to show there's no original thought. It's all incepted. Okay, 1, 2, 3, 4, 5. Okay, then this subset, right? Just any subset. We saw these ordered pairs, right? Is a relation from A into B. What are some of the things that we're forgetting? Well, we could look at 1 onto itself, 2 onto itself, 3 onto itself, 4 onto itself, 5 onto itself, blah, blah, blah. So here there could be 64 different ordered pairs that we could put into the subset, but I don't want to, let's not think about that quite yet. Okay, for now, it's just going to be a subset from this Cartesian product, which we know and love. Okay, why does this look like a matrix? Maybe just to me, kind of morphs into a matrix. If you have A times B, if you have 1, 2, 3, 4, 5, 1, 4, 1, 5, 2, 4, 2, 5, 3, 4. It's not really a matrix, but I guess it kind of is. Right? You could represent that as a matrix if you wanted to. Okay. So a relation is going to be a set of actions, I would say, where you're going from the first term to the second term. Okay? So it defines this relation, for lack of a better word. I think I included the divides because I thought it would be a bigger player, but we can talk about it, but it's not actually a huge player. So if it doesn't make sense, then we can get by without it. Okay. So if A and B are in the set of integers and A is not 0, okay, then we say that A divides B. Okay, that seems fair. Denoted by A divides B. If and only if there exists an integer k such that A times k is B, right? So A divides B if k is an integer because what? Because if A times k is equal to B, what I'm really interested in is whether B is divisible by A, or if A divides B, then that has to be equal. Whoa, that's so weird. Oh, I'm in the pencil. Then if B divided by A yields a K, but then the condition was that K is an integer. An integer is what? It's a whole number, right? And that's what we mean when we say that A divides B. It's a whole number. It can be negative, but ugh. It's apropos nothing, but I teach math for the water engineering technology, and they were making me rewrite my infinities this morning. We can't read those. I know they look like pancakes, but then someone said, well, what if you start on the other end? Then you get this kind of, well, that's kind of a lopsided one. That has nothing to do with us, but you can make me rewrite stuff. But only if it's like you can't read it. Sometimes I catch them myself. Number. But that's why I read it out. So I don't have to rewrite it. Okay, so if you kind of sit back and think about it, right, then if I tell you, okay, A divides B, then you would arrive at something like this, right? What does it mean if A divides B? Well, then the result of B divided by A must be some whole number, right? And so the divides function is one of the go-tos for illustrating relations. But like I said, it's not going to be a key player, so we don't need to worry about it too much. Okay. I didn't find this super helpful, but if you do, go for it. But that's why I didn't highlight it. What did I find helpful? Oh boy. Nope, not that. This exercise. So as I warned you, I guess is the right term, there's a lot of pretty heavy theory that we could be spending time on, but we don't build on it. We don't do anything with it. So I don't really see the point. But if you do, go for it. You can send me some questions to include on the test if you want. But I wasn't going to. But I do want you to do just something little bitty like this. I'll put it here. So like I said, we're only going to be dealing with ordered pairs for our relations. And so that's kind of a nice kind of training wheels. But for each of the following relations are defined on P, which is the set of positive integers, right? 1, 2, 3, 4, 5. Determine which of the given ordered pairs belong to R. Okay, and usually how we write it is X is related to Y. So this is how I read this. X is related to Y if and only if, I'll use the IFF, if and only if X divides, right? X divides Y. So that's the relation. So X is related to Y if and only if, maybe I should write that out. Said I wasn't going to. If and only if X divides Y. Okay. Remembering that in an ordered pair, you've got X comma Y, right? And also because X is related to Y, so X is the first entry and Y is the second entry. Now, all we need to do is out of this set, right? We need to figure out, well, which ones of these has an X that divides Y? Does 2 divide 3? No. Does 2 divide 4? Whee! Does 2 divide 8? Ta-da! Does 2 divide 17? Well, either way, no. I guess I shouldn't be so. Right. And so the set is going to be, and let me just make sure that I don't use different notation than they did in their, okay, they didn't set it up as a set. That's what I was worried about. 2, 4, and 2, 8 out of these options. Obviously, there are infinitely many more, right, on the set of P, positive integers, but out of this list, that's all we're concerned about. What about X is related to Y if and only if X is less than or equal to Y? Well, if X is 2, is it less than or equal to 3? Feeling good. Bing. If X is 3, is it less than or equal to 2? No. If x is 2, is it less than or equal to 4? Yes, it is. If x is 5, is it less than or equal to 8? Whee! So now we have 3 ordered pairs, 2, 3, 2, 4, and 5, 8 out of those options that satisfy that relation. Okay. The last one, x is related to y if and only if y is equal to x squared. Okay, so now we kind of have to read them in the opposite order. So 1 squared is 1, so that's good. 2 squared is 4, which is not 3, so 2 squared is 4, just like we said. So that one's good to go. 2 squared is still 4, which is not 6. So it's out. Which means that we have 1, 1 or 2, 4 in that relation. Nice. Trying to remember what I'm doing next. Digraphs, I think. Good memory. Good memory. We can graph relations, and that's where we're going to be spending the most of our time, is with these digraphs or directed graphs. Okay. So these are also called directed graphs. And they help us visualize relations on a set. Okay. So we're going to use them to find properties of relations. And there are quite a few properties. Wait, a few properties? Yeah. So for example, if we let some set A be 0, 1, 2, 3, so these are the elements that I have to choose from to create my relations, then a relation could be something like this. Now, this is just given to you, right? And same thing on the test, same thing on the final. I'll have something like this and I'll give you the relation, and then I'll ask you to do things with it, okay? And so what we do is we can visualize it with a graph, okay? And it's kind of a choose your own adventure thing, because it doesn't matter where you put the nodes. The nodes are these values, right? Those are the values that we have to play with, okay? And so it doesn't matter where you put them, you're just going to be graphing the relations between them, right? Given this relation here. Okay, so a couple of terms, and I think I highlighted it again. Okay, but the elements of A are called the vertices of the graph. Okay, and so here, if A has elements 0, 1, 2, 3, then I have a vertex at 0, a vertex at 1, a vertex at 2, and a vertex at 3. That layout is not obvious, right? To me, at least. I don't look at that and say, oh, of course that's where the 1 would go. What? Why would anyone put it there? Well, it doesn't matter. Usually what happens is you sketch out a relation and then you realize, oh, I could probably kind of straighten this out and make it easier to read if I just bend this this arm. You could bend it up here, right? Have 1 up here and it would look the same. Okay, so where the vertices are doesn't actually matter, right? It's the relationships between these points that matter. Okay. And so we use these arrows. So we connect vertex A to vertex B with an arrow, or which is also called an edge. Okay. And we only do that if there's a relationship between the two, right? And it has to be from the first point to the second point. Okay. Let me zoom in here. Okay. So if we have, they start off with a bang, right? 0, 0. What does that mean? It means you start at 0 and then you go back to 0, right? And so that's called a self loop at 0. Let's see here. Later, we're going to call that reflexive, but for now, it's just a self loop. And I was talking to Steve about if he had any fun examples for relations, because I mean, I do stats mostly. We don't do any of this. And he had a really cute example where these are all flights. So from Kelowna to Vancouver, let's go to Vegas, huh? Vegas. Cancun, anyone? Now we're talking, right? And so now you can go from Kelowna to Vancouver. Hey, this is looking more and more realistic. You have to go from Kelowna to Vancouver to Vegas. That kind of thing, right? And so they're just relationships between the nodes or the vertices. Okay, what's this flight? It's just going up in Kelowna, circling, going back down, which I've done from Vancouver. We left Vancouver, tried to fly into Kelowna, tried, flew back to Vancouver. Oh. And it was so late. And I slept at the airport that night. All right. That's neither here nor there. Well, it's here in the self loop. Now you'll remember. Poor Emily slept at the airport. It wasn't my first time, I assure you.
Sleep at the airport, you just like sleep on the seats, like they're not like,
Mm-hmm.
wow, very.
Yeah. And they make it super cold. So it's freezing. So I unpacked my bag and I just kind of piled it all over me. I've only slept at the airport twice. It's all part of being young. Now I don't sleep at airports anymore. Too old for that. Okay, I wasn't done with this. Okay. 0, 0, we got that one. There, I didn't finish. You almost let me move on. Sleeping at airports. 0, 3, how do we show that? Well, with a line going from 0 to 3. Notice that it's not going the other way necessarily, right? And so what would we need up here in order for it to go the other way? We would need 3, 0, right? But we don't. So there's only one way train here. 1 goes to 2. So 1 is down here for some reason and it goes to 2. Okay, we've got that. 2 goes to 1. So now we've got this. 2 goes to 1. Can go between the 2. That's good. 3 goes to 2. So and 2 goes to 0. And now you've got all your flight paths. Okay. And so a digraph is a visual representation of these relations. Okay. This is the same relation that we had down here, right? It's just you've rearranged your vertices a little bit, but the arrows are all the same, right? 1, 2, 2, 1, 0 goes to 0, 0 goes to 3, 3 goes to 2, 2 goes to 0. Same relations, different graph. New graph, who dis? A vertex is also called a node, point, or a junction. So any one of those terms can be used. I like to use node usually. But an edge of the graph, which is that line, call it a line, or an arc or a branch, whatever you want, okay? It also says, don't be concerned if two graphs of a given relation look different as long as the connections between vertices are the same in the two graphs. Okay, so it's all about how you interpret these vertices. And sometimes you work through a couple of iterations before you land on your final graph, right? But as long as the links are all the same, then you're good. Yeah. So if we have this, if I give you this directed graph, we can use it to find the relation. So the ordered pairs, right? It's gonna take some work. I'd rather not, but the original set that we're pulling from are the vertices, right? 1, 2, 3. So that's how we found that A is the set of 1, 2, 3. Those are our only options. These are our only airports, if you want to think of it that way. And then S is the relation. And if you work methodically through these, right, you can list all these values. So 1 to 2, 2 to 1, 1 to 3, 3 to 1, 2 to 3, 3 to 3. I'm out. I don't want to write all those out because they're here, right? So you can flip-flop between the two, you can have a relation, draw the digraph, right, to show the relation, or I can give you a graph and you can find the ordered pairs. Okay. My question is, how are we doing for time? Pretty good. Okay. Try doing this one. I'll just give you 2 minutes to try it. What are you going to start by doing? I say you're going to try it, but then I want to hold your hand the whole way. You're going to start by drawing out these 4 vertices, right? 1, 2, 3, 4. And then go forth.
We're just doing the brackets for all of them. The same we just did for the.
I want you to draw the graph. So do 1, 2. This is probably a bad setup. 3. But you can rearrange them once you've played around with them. You can list the pairs if you want to. I guess listing the pairs is the easier way to start. It'll work. Let me confirm something. So if we want the relation where the first term is less than or equal to the second term, right? Moving through, just working methodically through 1, 2, 3, 4, 1 is less than or equal to itself. So that's an option, right? So then I have 1, 1. 1 is less than or equal to 2 or 3 or 4. So I've got those all listed out. Right, and then I move on to 2. Well, 2 is not less than 1, so I know I'm focusing on the upper half. 2 is less than or equal to 2, so that's an option. 2, 3, 2, 4, 3, 3, 3, 3, 4, and then finally 4, 4. So we know from this diagonal that they're all going to have self loops, right? That's boring. We'll save those for. Well, that's exciting. We'll save those for last. How about that? Okay, so now if I have to draw these, I'm going to start, I'll use a different color just to highlight the ones. So 1 goes to 1, whoops. 1 goes to 2, 1 goes to 3, and 1 goes to 4. That's that first row visualized. What about the second row? So 2 goes to 2, whoop, self loop. 2 goes to 3, and 2 goes to 4. Nice. What a mess. 3 goes to 3, woo, and 3 goes to 4. These would all be the same color, obviously, but I just like to highlight which ones I'm doing. And then finally, if I haven't run out of colors, my self loop goes in different directions. That's weird. Guess you wouldn't even need an arrow. Just okay, so here's one option, right? But depending on how you move the vertices, it's going to look different, but the relations are all the same, right? Okay. How about the second one? So now we're drawing elements from 1, 2, 3, 4, 5. And we want to define T. Now T, that's just the name of the relation. Usually we stick to kind of R, S, T, those letters. T on A by ATB, if and only if B minus A is even. That's weird. Okay, so that's the condition. And A is the first term, B is the second term. And what we want is, we want all the ordered pairs where B minus A is even. Okay. What's one of the things that's going to help us solve this? Well, if I think about an odd minus an even, right? 1 minus 2, I'm going to get -1, which is odd, right? And so that's not going to work, right? But if I do 1 minus 3, which is 2 things away, right? I get -2, 1 minus, or I guess 3 minus 1, B minus A. Sorry about that. 3 minus 1 makes 2, which is even, right? And so the odds, I'm going to lump the odds together and I'm going to lump the evens together, because there's no way that I could go from an even to an odd and have the difference be even. Wow. Someone write that down. It's out of my head now, right? And so here, if B is odd, A must be odd. And if B is even, A must be even. For B minus A to be even, which is the condition that we're trying to get to. Okay. Do we want to write out the pairs or draw the graph? I don't know what's easier. Well, ultimately, we're going to draw the graph. Listing the pairs. I'm a little scared. Okay, fine. Fine. T is the set, okay, of elements where B minus A is even. So what I'm going to do is I'm going to do separate ones for the even numbers and the odd numbers. So let's start with the odd numbers. Okay, so if I have 3 minus 1, 3 minus 1 is 2, so that's even. So I can go from 1 to 3. That's allowed. Okay, 1 down. 1 to 3. Can I go from 1 to 5? Well, 5 minus 1 has to be even. 5 minus 1 is 4, which is even. All right, that's good. So I can go from 1 to 5. Can I go from 3 to 1? Why not? Right? 1 minus 3 is -2, which is still even. There's nothing about being positive or anything like that. We could have additional restraints, but I can go from 3 to 1, and by the same method, I can go from 5 to 1. Can I go from 3 to 5? Sure. I almost forgot about 3 to 5. 5 to 3? One to 1. Can I? Is 0 even a number? We do say 0 is a number in this case. So, and 0 is even. I'll make a note here. 0 is even. 0 is kind of a weird one, but I should have said that, given you the rules of the game before we played the game. 0 is even.
You don't like you.
0 minus 0 is 0. Hey, we're just about to do Boolean algebra. Have you guys done Boolean algebra? I don't know why I keep asking you if you've done all these things. We're going to do them. And it's super fun because all of a sudden you're back to 0 plus 0 is 0. 1 plus 1 is 1. Messes with you. I think it's 1. Or is 1 plus 1 0? Turn it on, turn it on, turn it off? No, turn it on. I don't know, we're not there yet. But 1 minus 1 is 0, which I just told you is even. So that's an option. Same thing with 3, 3, and 5, 5. Those are just the odds. We can do the same thing for the evens, but we only have 2 evens here, so that's fine. So let's go through and just double check those. So if I'm going from 2 to 4, then 4 minus 2 has to be even, which it is, right? And so that one goes on the list. 2 to 4, and by the same logic, 4 can go to 2, and 2 can go to 2, and 4 can go to 4. That's tricky. And let me add a page here. If you had to strategize a little bit on how you're going to draw this graph, right? You know you have to draw these vertices, 1, 2, 3, 4, 5. But we also see that there's no jump from an odd to an even. So what I'm going to do is I'm going to kind of separate the two. And so I want to do something like 1, 3, or maybe I should put them inside. Well, it's too late now. Like that, 5. No. How about like that? And then I'll do 2 and 4 over here, because they're going to have their own relations, right? We can't cross over if the difference has to be even. So now the fun part, guess I can't really color code these. Let's just go for it. 1 goes to 3. 1 goes to 5. 3 goes to 1. Woo! 5 goes to 1. Doo-doo. 3 goes to 5. 5 goes to 3. 1 goes to 1. 3 goes to 3. 5 goes to 5. Now that's super fun. Making the pairs not so much maybe, but once you've got them, I don't know. It's really fun. 2 to 4, 4 to 2. 2 birds with 1 stone. Boop, boop. And then on itself. Bink. So they're just, there's no relation between the odds and the evens, but there are relations between the two, right? Or within themselves. Nice. Okay. So a reflexive relation is when it's got that self loop. Okay. And so technically, let A be a set and let R be a relation on A, then R is reflexive if and only if A related to A for all A's in A. Oh boy. So that means that every, what's the saying in words? Every vertex has a self loop, right? Any element in A has a relation going onto itself or into itself, right? So this means every vertex has a self loop, right? Visually. Antisymmetry or antisymmetric relations, if A is a set and R is a relation on A, notice that that's generic, right? Then R, so the relation is antisymmetric if and only if whenever A is related to B and A is not B, so it's not itself, then B can't be related to A, right? And so what does that mean? It means that whenever, maybe I'll use green here, right? If we had to write this out in words, what would this look like on the graph? It means that whenever I have an arc, right, or a line, I'm not allowed to have a line going back, right? You're allowed to have a one-way ticket, but you can't go back, Hotel California style. Okay. Oh, how do I write that? If a vertex, or I guess I should say if 2 vertices, that's what I should say. If 2 vertices are connected by a line one way, there can't be a line going the other way. That's what it means to be anti-symmetric. Yeah. So here, another way to determine whether a relation is anti-symmetric is to examine or imagine its digraph. The relation is not anti-symmetric if there exists a pair of vertices, so 2 points that are connected by edges in both directions. So if there's even one where that's the case, then it's not anti-symmetric. The whole relation is not anti-symmetric, which confusingly doesn't mean it's symmetric, because that's another special thing. It's just not anti-symmetric. Okay, so here, kind of the same thing. Because I think that's the trickiest one to keep track of, is if something's anti-symmetric. But if you see any sort of two-way street, let's go back to, well, these are bad because they're all two-way streets. Let's go back to one that they drew, like this. If we didn't have this, we would consider it anti-symmetric, right? There's a one-way street. Oh, does the reflexive? No, it's fine. This is a one-way street. This is a one-way street, one-way street. But because we have this, it makes this relation not anti-symmetric. How about I snag this? And I'll put it down here. So here, this is what makes it not anti-symmetric. If we only had the other parts, we'd be fine. Or what else could we do? We could just erase one of these relations, right? Not sure which arc, but one of those would have to go, and then it would be anti-symmetric. Okay. The transitive relation is exactly like transitivity, it always is, right? If A is equal to B and B is equal to C, then A must be equal to C, right? And so let A be a set and let R be a relation on A, then R is transitive, okay? If and only if whenever A is related to B and B is related to C, then A must be related to C, right? If we have to think about, don't think about it too much. No, maybe, right? Consider general transitivity is if A is equal to B and B is equal to C. So if that and that, then A is equal to C. It's the same scenario, right? But now it's just with relations instead of values. That's a fun one. Okay. So what does that look like in terms of the graph? If I have just A and B and C, it's transitive if A is related to B, B is related to C, and then A is related to C. Two flights or one flight. Yeah. Okay. We introduce these concepts because they are all part of partial ordering. Now, a partial ordering is a special relation. So a relation on a set A that's reflexive, anti-symmetric, and transitive. So it has to be all those three things in order to be called a partial ordering. On A. Okay. And so there's lots of different terminology, but we'll just call it a partial ordering. So it has to be all those three things. Reflexive, oh yeah, self loop on all the vertices. Antisymmetric, only one-way flights. And transitive means that I have to be able to connect all the multi-stops into a one or a no-stop flight, a non-stop flight, some call it. All right. If you're interested, this is where they introduce a Hasse diagram, but we don't actually need it, but it's just a cleaner version of the partial ordering visualization. So if by definition they all have to have self loops, do we need to draw them? No. If by definition you can't have two-way streets, do you need an arrow? No, right? It's just going one way. And if it has to be transitive, then you can just connect them all. And that's how you get the Hasse diagram. But it just talks about what it does, but I'm ignoring them because we only need the one digraphs. They're complicated or more complicated, right? This is cleaner, but it works for us. Okay, so a symmetric relation is if and only if whenever A is related to B, then it follows that B must be related to A, right? And that has to be true for every line, right? So if there's a one-way, then you have to be able to take a flight back, right? And so if that's the case for every one-way, then you can say it's symmetric, right? The equivalence relation is kind of the same as the partial ordering, but it's got a different set of conditions. So a relation R on a set A is called an equivalence relation if and only if it's reflexive, symmetric, and transitive. So the only difference here being what? The symmetric instead of antisymmetric. Right, the other two are the same as the partial ordering. Right. Okay. Congruence modulos, no thank you. Ba, 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 ba. I had one picked out that I wanted to do. Okay, so or how much time do I have? How many sections? I think there's only one more thing. Let me just check. Yeah, but I don't give you a break, so I let you go a little early. Cool like that. Let me just double check. Oh, dang it. Okay, I forgot about closures. Okay. Then what we're going to do is I'll leave these with you, but what I want you to do is given a graph, and this is what I would expect on a test, on the final exam. If you have a graph, many graphs like this, can you identify if it's reflexive, antisymmetric, transitive, symmetric, and then use those properties to figure out if it's a partial ordering or an equivalence relation, right? Remembering which ones have to be checked, right? And so if you work through and figure out if they're reflexive, symmetric, antisymmetric, or transitive, for each of these, and then which of the graphs are of equivalence relations or of partial orderings. And then I'll post my solutions before I'll add my solutions to this one before I post the notes. Okay. A computer can't read a graph, right? You can't feed a graph. Here's a diagraph of this relation. It'll say, oh, no, thank you. But it can read a matrix, okay? And so what we can do is we can create this adjacency matrix or a relation matrix, if you want to think of it, of R. And that matrix is something that we can feed into a computer. Feed into it. No. But if we have a set A256, for example, then we can create this relation like this. And so what we want is we want to think of 2, 5, 6, 2, 5, 6, right? Those are the values that I'm drawing from. And 2, 2 is in the set, right? So that's in there. 2, 5, 2, 5 is in there. So, yep, I'm here. 5, 6 is the next one. 5, 6 is here. Home. And 6, 6 is there. The other ones are all off, right? And so they are going to be zeros. Right? And then you can kind of erase the outsides and put nice square brackets around it, or round if you're crazy. Make it a matrix, and there you go, right? And so that's how you would communicate these relations to a computer, right? Home, home, not home, not home, not home, home, not home, not home, home. Okay. I only bring it up because we're going to see it later. So we're going to work with Boolean arithmetic. But like I said, it's super fun. All of a sudden, 1 + 1 is 1, right? Boolean 0 1s. And so we're just working on 0 1. And we can define Boolean arithmetic. 0 + 0 is 0. 0 + 1 is 1. 1 + 1 is 1. 0 times 0 is 0. 0 times 1 is 0. 1 times 1 is 1, right? And so why would we need to know that? If we had to do matrix multiplication, that would be useful, right? Because then you're adding a bunch of 1s and 0s. We're skipping it. Had you going for a bit though. You could do it though, but why? Okay. The last thing that we're going to introduce here is the transitive closure. Remember, the transitivity is when you have multiple stops. You also have to have a nonstop flight, right? And so what we need to be able to do is figure out the closure of the set is basically the what's missing from the original set that would make it transitive. Okay, so if we let A be a set and R be a relation on A, blah blah blah, the transitive closure of R, which we denote by R plus, so I like to think of it as R with a little extra, is the smallest transitive relation that contains R as a subset. So usually for R plus, we just talk about what would be missing in order to have nonstop flights to places where I could get to with multiple stops. All right. So for example, if we're pulling from 1, 2, 3, 4, and this relation 1, 2, 2, 3, 3, 4 is a relation. Guess it's called a successor, but that's not important for us. Maybe it's important in life. 1, 2, 3, 4. Let's start out like that and see how it goes. I might have to rejig my graph. We'll see. So my original relation looks like this, right? I've got 1, 2, 2, 3, and 3, 4. Okay. I would need to add, what's an obvious flight I would need to add? How about 1, 3? I'd need that in order to have this transitive property, right? If 1 goes to 2 and 2 goes to 3, then 1 must go to 3, right? That's a transitive property. So I would add that to my closure, my transitive closure set. That's one of the options. What's another thing that's missing?
1 and 4.
Nice. Whee! The pickle is, if you've created more, I guess, multi-stop flights. So for example, if you had created 1, 3, then now all of a sudden 1, 3, 4 is a flight. We already were able to get to 4 from 1, so we had to do it anyways, but sometimes that's not the case. So then you would still have to create that flight. Okay. A relation, but flights are more fun, right? And so sometimes the more flights that you add, right, then you're gonna have to go back and make sure that you're not missing any. Am I missing any? 1 goes to 2, 2 goes to 3. Oh, yeah. Yowzas. Whee. It was over the equator. I had to go around. That's good though, I think. Sold. There might be more, I don't know. So then S plus is 1, 3, 1, 4, and 2, 4. As far as I can tell. Nice. Matrices, matrices. Can use matrix multiplication, but I say no thank you. And same thing. I want you to try this this exercise just for practice, but I'll include it in the notes when I post them. There you go. If you have any questions, let me know. Otherwise, have a wonderful weekend.
What- oh.